long-term development. Long-term, in this particular case, long duration. I spent about nearly 10 years without sound emulation and radar simulation in my calculators, because it was quite difficult. And the question is, what has this to do here? But when we have a look at Bernhard, he's using modern CPUs to replace old hardware. We have heard Sylvain about CL, it's nothing else, modern hardware on such a system. And of course, Michael with his Voyager series, it's always the same problem. In this particular case, I'm trying to use Windows as platform. Of course, the speed of a PC is much higher than a real calculator. But I have no real-time operating system, so it's sometimes really difficult to transform some functions to the platform. Especially when they say, why no sound? When I remember, many people say, so I have sound in IMO48 since the 90s. But this was a ROM patch. I patched the ROM with an illegal opcode. This illegal opcode was captured. Then I read from the registers the frequency and duration, and then using the operating system to replay the sound. Actually, it's now simulated, so no ROM patch is necessary. So that's a timetable. So my first tries with the sound emulation with IMO48 are done quite early, 1998, 99. But the sound, what I'm doing, because every opcode has a duration, and integrated the CPU cycles for each opcode. And when I want to restore the frequency, I just have a look at the position where the beeper was switching, and then look at the counting how many CPU cycles done since the last switch. That's the reason. But the countable values, the time was repeatable, and the counted CPU cycles has nothing to do with the frequency at all. So failed. Next timestamp was red eye decoding. I tried, I get a mail from Cyril Renaissance somewhere at this time with data sending from an HP48 to a printer, so with correction stems and so on. But he asked me how to implement this in IMO48. But who needs printing at IMO48? It's more interesting in IMO42 with the HP42S or 28S. And so I tried to implement this first in IMO42 because it's much more complex. There's no half-bit frame formatter and so on. But no success after about 20, 30, 40 decoded characters. I got only garbage and failed. Next step, 2011. I solved the problem with the red eye. You may ask why. In 2010, I was emulating or wrote mainly IMO71. And at the beginning of 2011, I had to write documentation, and I hate writing documentation about a new emulator. And so I was looking for something which are more interesting, and so I solved the problem. And the last one was the 3-bit beeper emulation implementation 2013. It was a posting, I think, from Gerson Barbosa in the forum. He asked me how to get sound in IMO71 for Windows. There was something. I wrote the ROM patch for beeping, but I haven't activated it. And so I thought about, okay, how you could solve this, because these problems, finished red eye implementation and finished beeper implementation, had the same reason why they don't work. Let's have a look at the red eye timing. Some of you may know it. We have here the 3 start bits, here 4 error correction bits, 8 data bits, interframe delay. Coding is it when we have a look at the 1. Each bit is divided in 2 halves, and if the ER signal is in the first half, it's a 1. If the ER signal is in the second half, it's a 0. This was done because of many reasons, because you have normally 2 types of errors. You may have noise or you may have dropouts. In this case, let's think about, okay, we have a 1 and we have noise. Then we have here a signal, and here a signal. Decoders say, well, that's illegal. I don't. It's not allowed to have bursts in both halves, and so it's a missing bit. If you have a dropout, same as well. Here no signal, here no signal. It's also not valid, so it's also illegal. And when you want to swap a byte, we must have, in the case of the 1 bit, here a dropout and here noise, and that's quite. It would it's not impossible, but quite rare. And because of this, when you have 2 missing bits, you can still restore the signal. Have a look at coding the burst signal. When you have here, we have a half-bit time of 427.525 microseconds. And when you counting these cycles, 7 cycles with the frequency of 32 kilohertz, that's exactly half of this complete frame time. This is generated by the CPU by this way. This is normally only a gate. This the frequency itself is coming from the crystal, from the clock crystal. And it's only a gate praktisch opening the signal to the infrared transmitter. So the CPU say, okay, start transmitting, wait the 200 and something microseconds, close the signal and it's waiting the rest, and then the half-bit with data inside has done. Second, of course, he must have the exact timing for a 0-bit. In this particular case, you have to wait the 427 microseconds without doing anything. So, the 30 kilohertz is generated by hardware, the other timing is done by the CPU. So, what has this problem with calculators? We have no hardware support on the Lewis chip. The 48 has the Clark chip, the Oct chip, there's a hardware formatted there, the CPU or the user had nothing to do with timing anymore. We have also no hardware support for the buzzer timing. It's also done by CPU cycles, waiting, the delay is completely done by CPU. The complete timing in must be generated by CPU core. The problem is the CPU strobe frequency, that is what we are speaking about, 1 MHz, 4 MHz, and so on. It's not crystal driven, so the timing is inaccurate. In the case of the 71, or in the case of the 18C or 28C, this is the first generation with the extra CPU 187, we have an LC oscillator there. And this is, of course, you can imagine, this is not very, very accurate. This is therefore, the calculator must measure the CPU speed from time to time, because especially for the red eye timing, red eye timing is very critical. And so we have solutions. We measure the CPU speed with a crystal-driven timer, because all of these calculators have a timer chip which has the 868 Hertz timer crystal. In the case of the 71, it's a 512 Hertz timer. In the case of all others, it's a higher timer. So when we measure the CPU, then the software creating timing tables from the results of this measuring. And from these timing tables, they create then the timings for setting infrared signal on, off, and so on. Okay, frequency measurement. I thought of when speed measurement, I thought about 100-meter race, for example. We have a fixed distance and measure the time. In this particular case, it's better to hold the time fixed, because the resolution, we can measure the times quite exact, but the resolution is not so high. And therefore, it's better to count the CPU cycles in a special frame. The frame in this particular case is 62.5 milliseconds. I will show you where it's come from. Internally, there's a loop counter, because I cannot measure the CPUs. So we have a loop internally. The loop is executed several times, and then when we count the CPU cycles of the loop, then we know the overall CPU counts of inside the time. So this is an extraction of the measure code from the 42S For those who want to have a look inside, the ROM is from ROM revision C, the addresses. So the first command here is the counting register. B is set to 0. Next, what we have is the time address. Normally the timer is F8, 8192. Because we're using the next one, it's divided by 16, so we are looking at a 500 Hertz counter value. Then he disables the keyboard scan because on the Saturn calculators the keyboard is activated and interrupts the CPU every 1 millisecond and so on. This is disabled. So now we're waiting that the time part of the time period starts, and because on the first time we may be somewhere inside this time frame, and so he is loading the timer value into the A register and then in the C register and comparing these both. When they're both equal, we are still inside in frame, and so when the C register changes here, then we continue the loop. So that we are really at the beginning of a new frame. Then it's a down counter. Then we are calculating our end result, so the end counter value. So in this particular case, CB is subtracted by 20 hex. So 20 hex are 32, so 512 divided by 32 are 16 Hertz, and these are these 62.5 milliseconds I spoke about. So here we have the increment measure command counter. Here's the loop counter, and now he's checking the register if the end value, which is now in C, is reached. If not, C is not equal A, I'm jumping here and make another count. So finally, when we have reached the end condition, we leave this loop. Here we have the CPU cycle counts, 6, 15, and these 15 is this opcode here is comparing and then jumping, has 15 opcodes. If he has to jump when the condition is not jumping at the last routine, it's not 15, it's 7. But in the normal case, each counting value means we have 30, 36 CPU cycles for each counting loop. So we know the stop cycle for each opcode, and so we can calculate the complete number of stop cycles in this frame. The value internally is stored by many of these calculators in the variable C speed. This is a RAM address. You can ask them, perhaps we can show you later when we have time, how you can read it on your calculator, because the nominal speed of a 71, for example, is given by 640 Hertz. But on my calculators and in my environment, I have only for 620, 621 kilohertz. I never reached the 640. Maybe it may be different in your country, but here. Yeah. What has this? What I spoke about relevance for emulation. When we are executing the calculator with original speed, doesn't matter anything. But when I have full speed, then my emulation runs about 50, 100, 200 times faster than the original calculator. And you can imagine what happens with the loop counter. It overflows. And so we see only the remainder of this loop, and the information is quite nothing. So the problem is that all frequency measurements in the calculator firmware return proper results when they measure the CPU frequency correctly. So you know, for example, you can speed up the 42 with to 2 megahertz, but then red eye isn't working anymore because we have only a very small frequency frame where the timing tables, the calculation of the timing table works. And so with these random numbers, the timing tables are completely defect. And so it may be that at the first time the frequency measurement was correct and so the encoding works, but because the timing is so accurate, the calculator, the 42 for example, do a recalculation of the CPU speed every 20 printed characters or something like that. And then when he returned a wrong CPU speed, and then if we question that we have these decoded garbage on this point. That was the reason. So the idea was then my emulator recognize the speed measurement condition because I don't want to fix or make a ROM patch to solve this, because this should run with the original ROM content. And so I'm watching the access to the timer value. The timer value is only accessed in a very, very short time frame on the condition of speed measurement, or in the case of waiting. So some there are waiting routines, and they're doing it by the same way. You're giving the time, and then he's waiting by this way. But in the case of waiting and in the case of speed measurements, I don't want to have the full speed. I switch back to original speed to get proper values, and then after I recognize that the measurement has been finished, I switch back to full speed. The problem of how decoding the red eye simulation is quite the same. I'm counting the CPU cycles, but now these are correct, and with the counting of the CPU cycles, I can decode it. It's a 1, it's a 0, and I'm decoding then the complete frame inside the emulator. That is of course not correct. Normally this decoding is doing the printer, and the transmitter only sends the thing, but I cannot transmit these internal signals over the operating system over to another exit program. So I do the decoding in the emulator and send the fully decoded signal over the UDP protocol to the receiver, to my printer simulation. The sound emulation works in the same way. I'm counting the CPU cycles with the known frequency. I know the time, and the time of 2 half timings give me the complete period, and then I know the frequency. The calculator is giving the output. But now I have the problem, of course, I have no real-time system. I cannot access the speaker by this way. So what I'm doing, I have internal buffers. In this particular case 20 milliseconds, where I prefetch the data. And after 60 milliseconds of collecting, I begin playing. In background, I collect further, and on the other side, I'm able to play with it. I done this also already when I still supported the Pocket PC platform. And there, the 20 milliseconds, because I have 3 buffers with 20 milliseconds each, so the 60 milliseconds, this was too short for them. There's internally somewhere a value where I can switch this value from 20 milliseconds to any other value when you have a very slow PC and you have interruptions, but I haven't seen this on Windows PC, on like modern or more or less modern Windows system, which would work without any modification. Questions?